Data Encryption Standard DES. In this video, we are going to see about Data Encryption Standard DES. Data Encryption Standard DES is a previously predominant symmetric key algorithm for the encryption of electric data. It was highly influential in the advancement of modern cryptography in the academic world. It is most widely used method of data encryption using a private key, that is secret key, that was judged so difficult to break by the US government that was restricted for exportation to other countries. DES adopted in 1977 by the National Bureau of Standards, now the National Institute of Standards and Technology, that is NIST, as Federal Information Processing Standard 46, FIPS PUB 46. The algorithm itself is referred to as the Data Encryption Algorithm, DEA. For DES, data are encrypted in 64-bit blocks using a 56-bit key. The algorithm transforms 64-bit input in a series of steps into a 64-bit output. The same steps with the same key are used to reverse the encryption. The DES enjoys widespread use. It has also been the subject of much controversy concerning how secure the DES is. To appreciate the nature of the controversy, let us quickly review the history of the DES. To accomplish encryption, most secret key algorithms use two main techniques known as substitution and permutation. Substitution is simply a mapping of one value to another, whereas permutation is a reordering of the bit positions for each of the inputs. These techniques are used a number of times in iterations called rounds. Generally, the more rounds there are, the more secure the algorithm. A non-linearity is also introduced in the encryption so that decryption will be computationally infeasible without the secret key. This is achieved with the use of S-boxes, which are basically nonlinear substitution tables where either the output is smaller than the input or vice versa. One of the main problems with the secret key cryptography is key distribution. For this form of cryptography to work, both parties must have a copy of the secret key. This would have to be communicated over some secure channel, which unfortunately is not that easy to achieve. DES uses both the transposition and substitution, and for that reason is sometimes referred to as a product cipher. Its input, output, and key are each 64 bits long. The output of the 16th round consists of 64 bits that are a function of the input plain text and the key. Advantages: as 56-bit keys are used, there are 70 quadrillion possible key values, and hence a specific key cannot be identified easily. As the length of the key is increased, the security provided by the algorithm also increases. The security of the DES algorithm resides in the key. Disadvantages: as it is a symmetric algorithm, both sender and receiver must have same key. There is a possibility that the key is intercepted. The design of S-boxes makes it susceptible to linear cryptanalysis attack. It is susceptible to different cryptanalysis attack and brute force attack, taking advantage of which DES crackers have been designed. It has certain weak keys which generate the same key for all the cycles of the algorithm, like when all key bits are either zeros or ones, or if one half of the key bits are zeros or ones. They are 000, 0000, 000, 000, 0000, 0000, FFF, FFFF, FFF, FFFF, 000, 0000, FFF, FFFF, FFF, FFFF. Some initial keys produce only 2 subkeys, while some produce only 4. They are called possible weak keys. DES encryption. In this video, we are going to see about DES encryption. As with any encryption scheme, there are 2 inputs to the encryption function, the plaintext to be encrypted and the key. In this case, the plaintext must be 64 bits in length and the key is 56 bits in length. Looking at the left-hand side of the figure, we can see that the processing of the plaintext proceeds in 3 phases. Key generation techniques. First, the 64-bit plaintext passes through an initial permutation IP that rearranges the bits to produce the permuted input. This is followed by a phase consisting of 16 rounds of the same function, which involves both permutation and substitution functions. The output of the last, that is 16th round, consists of 64 bits that are a function of the input plaintext and the key. The left and right halves of the output are swapped to produce the pre-output. Finally, the pre-output is passed through a permutation IP-1, that is the inverse of the initial permutation function, to produce the 64-bit ciphertext. The right-hand portion of above figure shows the way in which the 56-bit key is used. Initially, the key is passed through a permutation function. Then for each of the 16 rounds, a subkey Ki is produced by the combination of a left circular shift and a permutation. The permutation function is the same for each round, but a different subkey is produced because of the repeated shifts of the key bits. Initial permutation. The 64 entries in the permutation table contain a permutation of the numbers from 1 to 64. Permutation tables for DES. Each entry in the permutation table indicates the position of a numbered input bit in the output, which also consists of 64 bits. Initial permutation IP. Inverse initial permutation IP-1. Expansion permutation E. Permutation function P. To see that these 2 permutation functions are indeed the inverse of each other, consider the following 64-bit input M. Where Mi is a binary digit, then the permutation is as follows. If we then take the inverse permutation, y is equal to IP-1 of x is equal to IP-1 of IP of m, it can be seen that the original ordering of the bits is restored. Single round DES encryption algorithm. The left and right halves of each 64-bit intermediate value are treated as separated 32-bit quantities labeled as L left and R right. As in any classic physical cipher, the overall processing at each round can be summarized in the following formulas. Ri is equal to Li-1 XOR f of Ri-1, Ki. Li is equal to Ri-1 S boxes in the function. Selecting entry in X box. S box value for DES. The round key Ki is 48 bits. The R input is 32 bits. This R input is first expanded to 48 bits by using a table that defines a permutation plus an expansion that involves duplication of 16 of the R bits. The resulting 48 bits are XORed with Ki. This 48-bit result passes through a substitution function that produces a 32-bit output. The substitution consists of a set of 8 S boxes, each of which accepts 6 bits as input and produces 4 bits as output. The first and last bits of the input to box Si form a 2-bit binary number to select one of 4 substitutions defined by the 4 rows in the table for Si. The middle 4 bits select one of the 16 columns. The decimal value in the cell selected by the row and column is then converted to its 4-bit representation to produce the output. For example, in S1, for input 011001, the row is 01 row 1 and the column is 1100, that is column 12. The value in row 1, column 12 is 9, so the output is 1001. Each row of an S box defines a general reversible substitution. If you examine the expansion table, you see that the 32 bits of input are split into groups of 4 bits and then become groups of 6 bits by taking the outer bits from the 2 adjacent groups. For example, if part of the input word is E, F, G, H, I, J, K, L, M, N, O, P, this becomes D, E, F, G, H, I, J, K, L, M, L, M, N, O, P, Q. DES key schedule. The DES key schedule generates the subkeys needed for each data encryption round. The 64-bit key input is first processed by permuted choice 1. The resulting 56-bit key is then treated as two 28-bit quantities C and D. In each round, these are separately processed through a circular left shift rotation of 1 or 2 bits. These shifted values serve as input to the next round of the key schedule. They also serve as input to permuted choice 2, which produces a 48-bit output that serves as input to the round function f. The extra 8 bits were then used as parity, that is error detecting bits, which makes sense given the original design used for hardware communication links. It forms subkeys used in each round and consists of initial permutation of the key PC1, which selects 56 bits in two 28-bit halves. Input key. 16 stages consisting of selecting 24 bits from each half, permuting them by PC2 for use in function f. Permuted choice 1, PC1. Permuted choice 2, PC2. Rotating each half separately, either 1 or 2 places depending on the key rotation schedule K. Schedule of left shifts. DES key generation. 64-bit key is used as input to the algorithm. The initial 64-bit key is transformed into a 56-bit key by discarding every 8th bit of the initial key. From 56-bit key, a different 48-bit subkey is generated during each round using a process called as key transformation. The resulting 56-bit key is then treated as two 28-bit quantities labeled C0 and D0. At each round, Ci-1 and Di-1 are separately subjected to a circular left shift or rotation of 1 or 2 bits. These shifted values serve as input to the next round. They also serve as input to permuted choice 2, which produces a 48-bit output that serves as input to the function f of ri-1, ki. DES decryption. In this video, we are going to see about DES decryption. DES decryption. As with any pistol cipher, decryption uses the same algorithm as encryption, except that the application of the subkeys is reversed order, SK16 and so on up to SK1. Note that IP undoes final FP step of encryption. First round with SK16 undergoes 16th encrypt round, 16th round with SK1 undoes first encrypt round, and then finally FP undoes initial encryption IP, thus recovering original data value. The permutation IP-1 applied to the pre-output block is the inverse of the initial permutation IP applied to the input. Consequently, to decipher, it is only necessary to apply the very same algorithm to an enciphered message block, taking care that at each iteration of the computation, the same block of key bits k is used during decipherment as was during the encipherment of the block, only in a reverse order. For the decipherment calculation with R10L10 as the permuted input, K10 is used in the first iteration, K10 in the second, and so on, with K used in the 16th iteration. DES weak keys. With many block ciphers, there are some keys that should be avoided because of reduced cipher complexity. These keys are such that the same subkey is generated in more than one round, and they include weak keys, semi-weak keys, demi-semi-weak keys. Weak keys. Weak keys is same subkey is generated for every round, and DES has 4 weak keys. Semi-weak keys. Only 2 subkeys are generated on alternate rounds, and DES has 12 of these in 6 pairs. Demi-semi-weak keys have 4 subkeys generated. Multiple encryptions. In this video, we are going to learn about multiple encryption. Multiple encryption would preserve the existing investment in software and equipment, is to be used with data encryption standard DES and multiple keys. Clear replacement for DES was needed. Theoretical attacks that can break it. Demonstrated exhaustive key search attacks. AES is a new cipher alternative. Prior to this alternative was to use multiple encryption with DES implementations. Triple DES is the chosen form and widely accepted approach. One approach is to design a completely new algorithm, of which AES is a prime example. Another alternative which would preserve the existing investment in software and equipment is to use multiple encryptions with DES and multiple keys. Issue of reduction to single stage and have meet in the middle attack. Works whenever use a cipher twice, since x is equal to ek1 of p is equal to dk2 of c. Attack is made by encrypting p with all keys and store, then decrypt c with keys and match x value. It takes order of 2^56 steps. Double Data Encryption Standard, double DES. In this video, we are going to see about Double Data Encryption Standard, double DES. Double Data Encryption Standard, double DES. The simplest form of multiple encryptions has 2 encryption stages and 2 keys, double DES. The encryption process could use 2 DES encryption on each block for a given a plaintext P and 2 encryption keys K1 and K2. Ciphertext C is generated as C is equal to E of K2, E of K1, P. Decryption requires that the keys be applied in reverse order. P is equal to D of K1, D of K2, C. For DES, this scheme apparently involves a key length of bits, resulting in a dramatic increase in cryptographic strength. But we need to examine the algorithm more closely. Reduction to a single stage. Suppose it were true for DES. For all 56-bit key values that given any two keys K1 and K2, it would be possible to find a key K3 such that EK2 of EK1 of P is equal to EK1 of P. If this were the case, then double encryption and indeed any number of stages of multiple encryption with DES would be useless because the result would be equivalent to a single encryption with a single 56-bit key. Consider that encryption with DES is a mapping of 64-bit blocks to 64-bit blocks. In fact, the mapping can be viewed as a permutation. That is, if we consider all 264 possible input blocks, DES encryption with a specific key will map each block into a unique 64-bit block. Otherwise, if, say, two given inputs mapped to the same output block, then decryption to recover the original plaintext would be impossible. With 264 possible inputs, how many different mappings are there that generate a permutation of the input blocks? The value is easily seen to be 264 factorial is equal to 10347380000000000 greater than 10 power 10 to the power 20. On the other hand, DES defines one mapping for each different key for a total number of mappings. 2 power 56 is lesser than 10 power 17. Therefore, it is reasonable to assume that if DES is used twice with different keys, it will produce one of the many mappings that is not defined by a single application of DES. Although there was much supporting evidence for this assumption, it was not until 1992 that the assumption was proved, CAMP 92. Meet-in-middle attack. Thus, the use of double DES results in a mapping that is not equivalent to a single DES encryption. But there is another way to attack this scheme, one that does not depend on any particular property of DES, but that will work against any block encryption cipher. The algorithm known as meet-in-the-middle attack was first described in DIFF 77. It is based on the observation that if we have C is equal to EK2 of EK1 of P, then X is equal to EK1 of P is equal to DK2 of C. Given a known pair PC, the attack proceeds as follows. First, encrypt P for all 256 possible values of K1. Store these results in a table and then sort the table by the values of X next. Decrypt C using all 2 power n possible values of K2. As each decryption is produced, check the result against the table for a match. If a match occurs, then test the two resulting keys against a new known plaintext ciphertext pair. If the two keys produce the correct ciphertext, accept them as the correct keys. For any given plaintext P, there are 2 power possible ciphertext values that could be produced by double DES. Double DES uses in effect a 112-bit key so that there are 2 power 112 possible keys. Therefore, on average, for a given plaintext P, the number of different 112-bit keys that will produce a given ciphertext C is 2 power 112 divided by 2 power 64, which is equal to power 248. A similar argument indicates that with an additional 64 bits of known plaintext and ciphertext, the false alarm rate is reduced to 248 minus 64, which is equal to 216. Put another way, if the meet-in-the-middle attack is performed on 2 blocks of known plaintext ciphertext, the probability that the correct keys are determined is 1 to 216. The result is that a known plaintext attack will succeed against double DES, which has a key size of 112 bits with an effort on the order of 256, not much better than 2 PAR required for single DES. Triple Data Encryption Standard Triple DES. In this video, we are going to see about Triple Data Encryption Standard Triple DES. In cryptography, Triple DES. Triple DES is a common name for the triple data encryption algorithm symmetric key block cipher, which applies data encryption standard DES cipher algorithm 3 times to each data block. This original DES cipher's key size of 56 bits was generally sufficient when that algorithm was designed, but the availability of increasing computational power made brute force attacks feasible. Triple DES provides a relatively simple method of increasing the key size of DES to protect against such attacks without the need to design a completely new block cipher algorithm. Given the potential vulnerability of DES to a brute force attack, there has been considerable interest in finding an alternative. One approach is to design a completely new algorithm, of which several examples are given. Another alternative, which would preserve the existing investment in software and equipment, is to use multiple encryption with DES and multiple keys. We begin by examining the simplest example of this second alternative. We then look at the widely accepted Triple DES approach. Triple DES with 2 keys. Triple DES with 2 keys is a popular alternative to single DES, but suffers from being 3 times slower to run. The uses of encryption and decryption stages are equivalent, but the chosen structure allows for compatibility with single DES implementations. 3DES with 2 keys is a relatively popular alternative to DES and has been adopted for use in the key management standards ANSI X 9.17 and ISO 8732. Currently, there are no practical cryptanalytic attacks on Triple DES. Coppersmith notes that the cost of a brute force key search on Triple DES is on the order of 2 PAR 112, which is equal to 5 into 10 PAR 33, and estimates that the cost of differential cryptanalysis suffers an exponential growth compared to single DES, exceeding 10 PAR 52. Triple DES must use 3 encryptions, need 3 distinct keys, but can use 2 keys with encryption, decryption, encryption sequence, EDE sequence. C is equal to E of K1, D of K2, E of K1, P. P is equal to D of K1, E of K2, D of K1, C. The decryption of Triple DES is in reverse order. There is no cryptographic significance to the use of decryption for the second stage. Its only advantage is that it allows users of Triple DES to decrypt data encrypted by users of the older single DES. C is equal to E of K1, D of K1, E of K1, P is equal to E of K1, P. P is equal to D of K1, E of K1, D of K1, C, which is equal to D of K1, C. Encrypt and decrypt equivalent in security. If K1 is equal to K2, then can work with single DES. Standardized in ANSI X 9.17 and ISO 8732. No current known practical attacks. Several proposed impractical attacks might become basis of future attacks. A known plaintext attack is outlined in WANO 90. This method is an improvement over the chosen plaintext approach but requires more effort. The attack is based on the observation that if we know A and C, then the problem reduces to that of an attack on double DES. Of course, the attacker does not know A, even if P and C are known, as long as the two keys are unknown. However, the attacker can choose a potential value of A and then try to find a known P-C pair that produces A. The attack proceeds as follows. Obtain n of P-C pairs. This is the known plaintext. Place these in a table sorted on the values of P. Pick an arbitrary value for A and create a second table with entries defined in the following fashion. For each of the 256 possible keys, K1 is equal to I, calculate the plaintext value Pi that produces Pi is equal to D of I, A. Triple DES with 3 keys. Thus, the use of double DES results in a mapping that is not equivalent to a single DES encryption. Thus, many researchers now feel that 3-key triple DES is the preferred alternative, for example, Kali 96. 3-key triple DES has an effective key length of 168 bits and is defined as follows. C is equal to EK3 of DK2 of EK1 of P. Backward compatibility with DES is provided by putting K3 is equal to K2 or K1 is equal to K1. A number of internet-based applications have adopted 3-key triple DES, including PGP and S/MIME. Types of attacks on encrypted messages. In this video, we are going to see about types of attacks on encrypted messages. The various types of cryptanalyst attacks based on the amount of information known to the cryptanalyst are as follows. Attacks of encryption schemes. We can divide attacks roughly into 2 classes: passive attack, active attack. Passive attack. A passive attack is one in which the attacker is only able to monitor the communications channel. Threatens confidentiality only. Passive attacks can be further subdivided: ciphertext only attacks, known plaintext attacks, chosen plaintext attack, chosen ciphertext attack, adaptive chosen ciphertext attack. Ciphertext only attacks. It attempts to deduce the plaintext from the ciphertext only. Less chance to succeed against the strong encryption. Known plaintext attacks. It is the attack that has access to a collection of plaintext messages and their corresponding ciphertext. If same key is used to encrypt multiple blocks, chances of finding the key is possible. Chosen plaintext attack. A chosen plaintext attack is called adaptive if the attacker can choose the ciphertext depending on previous outcomes of the attack. Goal: learn something about other ciphertexts. This can be used to acquire a signed message like "Please authenticate me." Chosen ciphertext attack. Chosen ciphertext attack (CCA) is an attack model for cryptanalysis in which the cryptanalyst gathers information, at least in part, by choosing a ciphertext and obtaining its decryption under an unknown key. The attacker selects the ciphertext, sends it to the victim, and is given in return the corresponding plaintext or some part. Adaptive chosen ciphertext attack. An adaptive chosen ciphertext attack CCA2 is an interactive form of chosen ciphertext attack in which an attacker sends a number of ciphertexts to be decrypted, then uses the result of these decryptions to select subsequent ciphertext. The goal of this attack is to gradually reveal information about an encrypted message or about the decryption key itself. Active attacks. An active attack is the one in which the attacker attempts to add, delete, or modify messages. Threatens both confidentiality and data integrity. Active attacks can be further subdivided: known key attack, replay attack. Known key attack. The attacker obtains previously used keys and uses this to deduce information about new keys. Tracks generation of pseudo-random numbers. Replay attack. An attacker records a communication session and replays part of it at a later time. Login, key exchange. Impersonation. Attacker assumes the identity of one or more members of the network. Reflection attack. A and B want to synchronize with secret keys. A sends a challenge to B. A to M1 to B. B to E of M1, M2 to A. A to M2 to B. Intruder intercepts, pretends to be B, initiating the same protocol. Dictionary. Attacker uses a large list of words to deduce a password. Unix password attacks. Forward search. Brute force search of key space. Consider this authentication protocol. A sends random number M1 to B. A sends M1 to B. B returns random numbers M1 and M2 signed plus an identifier. M2 returns A. B returns SB of M2, M1, A. A returns signed random numbers M2 and M3 plus an identifier. A sends M3, SA of M3, M2, B sends to B. Intent. Random numbers plus signatures will verify identity. An enemy E can initiate two separate protocols with A and B. E sends M1 to B. M2 returns to E. B returns SB of M2, M1, A. E returns M2 to A. A sends M3, SA of M3, M2, B sends to E. E sends M3, SA of M3, M2, B sends to B. Insecurity due to symmetry of messages could vary structure or require M1 to be included in final message. Attacking key exchange. A sends B its public key. Man in the middle replaces A's public key with a false one. Man in the middle is now able to intercept and decrypt secret messages from B to A. Attacks on DES. In this video, we are going to see about attacks on DES. The statistical attacks, which depend on the amount of information gathered for their likelihood of success, now have several analytic attacks on DES. These utilize some deep structure of the cipher. By gathering information about encryptions, can eventually recover some or all of the sub-key bits. If necessary, then exhaustively search for the rest. Generally, these are statistical attacks, differential cryptanalysis, linear cryptanalysis, related key attacks. Differential cryptanalysis. Differential cryptanalysis can be successfully used to cryptanalyze the DES with an effort on the order of 2^47 encryptions requiring 2^47 chosen plaintext. This form of attack on a variety of encryption algorithms and hash functions can be carried out. Differential cryptanalysis was known to the IBM DES design team as early as 1974 as a T-attack and influenced the design of the S-boxes and the permutation P to improve its resistance to differential cryptanalysis. The attack is performed by repeatedly encrypting plaintext pairs with known input XOR until obtain desired output XOR pairs. When found, if intermediate rounds match required XOR, have a right pair. If not, then have a wrong pair. Relative ratio is S/N for attack. It can then deduce key values for the rounds. Right pairs suggest same key bits. Wrong pairs give random values. For large number of rounds, probability is so low that more pairs are required than exist with 64-bit inputs. Beham and Shamir have shown how a 13-round iterated characteristic can break the full 16-round DES. Differential cryptanalysis is a chosen plaintext attack that analyzes how the differences in two plaintext messages affect the differences between the corresponding ciphertext. Assume attacker has a large number of tuples X group, Y group, where X dash is equal to X XOR with X group is fixed. It is similar to linear attack. The main difference from linear cryptanalysis is that differential cryptanalysis involves comparing the XOR of two inputs to the XOR of the corresponding two outputs. The expansion function E and the final permutation function P are easily invertible, so they can essentially be ignored. We can also ignore the sub-key XOR stage of the F function. Proof. Suppose we take two inputs to the F function M1, M2. It is differ by a known amount delta 1. Consider bit strings message as elements of Z2 power 32. M2 is equal to M1 plus del 1 is equal to M1 XOR del 1. After inputs XOR with the key bits, M1 XOR K XOR with M2 XOR K is equal to M1 XOR M2 is equal to del 1. So the two inputs retain their difference even after being mixed with the key bits. The table described is called the pairs XOR distribution table. Each row of the table represents an input XOR value and each column represents an output XOR value. The table entries represent the number of possible pairs with such an input XOR and such an output XOR. The pair is called differential. Linear cryptanalysis. A more recent development is linear cryptanalysis. This attack is based on finding linear approximations to describe transformations performed in DES. It is also a statistical method which must be iterated over rounds with decreasing probabilities. It was developed by Matthew et al. In early 90s based on finding linear approximations. It can attack DES with 2 power 43 known plaintext, easier but still in practice infeasible. This method can find a DES key given 2 power 43 known plaintext as compared to 2 power 47 chosen plaintext for differential cryptanalysis. Although this is a minor improvement because it may be easier to acquire known plaintext rather than the chosen plaintext, it still leaves linear cryptanalysis infeasible as an attack on DES. Strength of DES: timing attacks. Timing attack is one in which information about the key or the plaintext is obtained by observing how long it takes a given implementation to perform decryptions on various ciphertexts. A timing attack exploits the fact that an encryption or decryption algorithm often takes slightly different amounts of time on different inputs. Timing attack use knowledge of consequences of implementation to derive information about some or all subkey bits, specifically use fact that calculations can take varying times depending on the value of the inputs to it. Timing attack is particularly problematic on smart cards. Brute force attack. The main idea of brute force attack is systematically checking all possible keys until the correct key is found. In the worst case, this would involve traversing the entire search space. It will always find a solution. A brute force attack is a trial and error method used to obtain information such as a user password or personal identification number, that is PIN. In a brute force attack, automated software is used to generate a large number of consecutive guesses as to the value of the desired data. Brute force attacks may be used by criminals to crack the encrypted data or by security analysis to test an organization's network security. A brute force attack may also be referred to as brute force cracking. Advanced Encryption Standard AES. In this video, we are going to see about Advanced Encryption Standard AES. The Advanced Encryption Standard AES was published by NIST, that is, National Institute of Standards and Technology, in 2001. AES is a symmetric block cipher that is intended to replace DES as the approved standard for a wide range of applications. The AES cipher and other candidates forms the latest generation of block ciphers, and now we see a significant increase in the block size from the old standard of 64 bits up to 128 bits and keys from 128 to 256 bits. Whilst triple DES is regarded as secure and well understood, it is slow, especially in software. In a first round of evaluation, 15 proposed algorithms were accepted. A second round narrowed the field to 5 algorithms. NIST completed its evaluation process and published a final standard, that is FIPS PUB 197, in November 2001. NIST selected Rigendale as the proposed AES algorithm. The two researchers who developed and submitted Rigendale for the AES are both cryptographers from Belgium, Dr. John Damon and Dr. Vincent Regimen. AES evaluation criteria. AES criteria span the range of concerns for the practical application of modern symmetric block ciphers. In fact, two sets of criteria evolved: initial criteria, final criteria. Initial criteria. The initial criteria stated that candidate algorithms would be compared based on the factors such as security, cost, algorithm and implementation characteristics. Security. This refers to the effort required to cryptanalyze an algorithm. Following parameters are also considered for evaluation: actual security, randomness, cost, licensing requirements, computational efficiency, memory requirements, algorithm and implementation characteristics. This category includes a variety of considerations including flexibility, simplicity. Final criteria. The final criteria evolved during the evaluation process includes general security, ease of software and hardware implementation, implementation attacks, flexibility in encrypt or decrypt, keying, other factors. AES cipher. In this video, we are going to see about AES cipher. Like DES, AES is a symmetric block cipher. This means that it uses the same key for both encryption and decryption. However, AES is quite different from DES in a number of ways. The algorithm Regendale allows for a variety of block and key sizes and not just the 64 and 56 bits of DES block and key size. The block and key can in fact be chosen independently from 128, 160, 192, 224, 256 bits and need not be the same. However, the AES standard states that the algorithm can only accept a block size of 128 bits and a choice of 3 keys, that is 128, 192, 256 bits. Depending on which version is used, the name of the standard is modified to AES 128, AES 192 or AES 256 respectively. A number of AES parameters depend on the key length. For example, if the key size used is 128, then the number of rounds is 10, whereas it is 12 and 14 for 192 and 256 bits respectively. At present, the most common key size likely to be used is the 128-bit key. The description of the AES algorithm therefore describes this particular implementation. Characteristics: resistance against all known attacks, speed and code compactness on a wide range of platforms, design simplicity. AES block. The input to the AES encryption and decryption algorithms in a single 128-bit block as a square matrix of bytes. The block is copied into the state array, which is modified at each stage of the encryption or decryption. After the final stage, state is copied to an output. It has 9, 11, 13 rounds in which state undergoes byte substitution, 1s box used on every byte. Shift rows, permute bytes between groups or columns. Mix columns, subs using matrix multiply of groups. Add round key, XOR state with key material. AES encryption and decryption. In this video, we are going to see about AES encryption and decryption. The step for encryption is proceeded downwards and decryption process is proceeded upwards. AES instead processes the entire data block as a single matrix during each round using substitutions and permutations. The key that is provided as input is expanded into an array of 44 32-bit words W of I. 4 distinct words, that is 128 bits, serve as the round key for each round. 4 different stages are used, 1 of permutation and 3 of substitution. Substitute bytes uses an S box to perform a byte-by-byte substitution of the block. Shift rows, a simple permutation. Mix columns, a substitution that makes use of arithmetic over. Add round key, a simple bitwise XOR of the current block with a portion of the expanded key. The structure is quite simple. For both encryption and decryption, the cipher begins with an add round key stage followed by 9 rounds that each includes all 4 stages followed by a 10th round of 3 stages. Only the add round key stage makes use of the key. For this reason, the cipher begins and ends with an add round key stage. Any other stage applied at the beginning or end is reversible without knowledge of the key and so would add no security. The add round key stage is in effect a form of Vernam cipher, and the cipher is an alternating operations of XOR encryption, that is add round key of a block followed by scrambling of the block, that is the other 3 stages, and followed by XOR encryption and so on. This scheme is both efficient and highly secure. Each stage is easily reversible. For the substitution byte, shift rows, and a mix column stage, an inverse function is used in the decryption algorithm. For the add round key stage, the inverse is achieved by XORing the same round key to the block using the result that A XOR B is equal to A. As with most block ciphers, the decryption algorithm makes use of the expanded key in reverse order. However, the decryption algorithm is not identical to the encryption algorithm. This is a consequence of the particular structure of AES. Once it is established that all 4 stages are reversible, it is easy to verify that decryption does recover the plaintext. At each horizontal point, state is the same for both encryption and decryption. The final round of both encryption and decryption consists of only 3 stages. Again, this is a consequence of the particular structure of AES and is required to make the cipher reversible. Substitute bytes. There is a single 8-bit wide S box used on every byte. This S box is a permutation of all 256 8-bit values constructed using a transformation which treats the values as polynomials in GF of 2 power 8. However, it is fixed, so really only need to know the table when implementing. Decryption requires the inverse of the table. A simple substitution of each byte uses one S box of 16 cross 16 bytes containing a permutation of all 256 8-bit values. Each byte of state is replaced by byte indexed by row, that is left 4 bits, and column, right 4 bits. Example: byte 95 is replaced by byte in a row 9, column 5, which has the value 2A. S-box constructed using defined transformation of values in GF of 256. It is designed to be resistant to all known attacks. Shift row transformation. This step provides permutation of the data, whereas the other steps involve substitutions. A circular byte shift in each first row is unchanged. Second row does 1 byte circular shift to left. Third row does 2 byte circular shift to left. Fourth row does 3 byte circular shift to left. Decrypt inverts using shifts to right. Since state is processed by columns, this step permutes bytes between the columns. The simple routine, which performs a forward shift row transformation, involves: the first row of state is not altered. For the second row, a 1 byte circular left shift is performed. For the third row, a 2 byte circular left shift is performed. For the fourth row, a 3 byte circular left shift is performed. Mixed columns transformation. This step is also a substitution, but one involving all values in a column, designed as a matrix multiplication, where each byte is treated as a polynomial in GF of 2 power 8. The inverse used for decryption involves a different set of constants. The constants used are based on a linear code with maximal distance between code words. This gives good mixing of the bytes within each column. Combined with the shift row step provides good avalanche, so that within a few rounds, all output bits depend on all input bits. Each column is processed separately. Each byte is replaced by a value dependent on all 4 bytes in the column. Effectively, a matrix multiplication in GF of 2 power 8 using prime polynomial m of x is equal to x power 8 plus x power 4 plus x power 3 plus x plus 1. Each element in the product matrix is the sum of products of elements of one row and one column. In this case, the individual additions and multiplications 5 are performed in GF of 2 power 8. The mixed columns transformation of a single column j 0 less than or equal to j less than or equal to 3 of state can be expressed as: the above figure shows the matrix transformation for mixed column matrix multiplication on state. Can express each column of the new state as 4 equations. One equation is used to derive each new byte in column. Decryption requires use of inverse matrix with larger coefficients, hence a little harder. Add round key. In the forward add round key transformation called add round key, the 128 bits of state are bitwise XORed with the 128 bits of the round key. The operation is viewed as a column-wise operation between the 4 bytes of a state column and 1 word of the round key. It can also be viewed as a byte-level operation, that is, processed by column, though effectively a series of byte operations. AES key expansion. Key expansion is designed to be simple to implement, but by using round constants break symmetries and make it much harder to deduce other key bits if just some are known, but ones have as many consecutive bits as are in key, can then easily recreate the full expansion. It takes 128-bit 16-byte key and expands into array of 44, 52, 60, 32-bit words. Start by copying key into first 4 words, then loop creating words that depend on values in previous 4 places back In 3 of 4 cases, just XOR these together. First word in 4 has rotate plus sbox plus XR round constant on previous before XR fourth. AES decryption. AES decryption is used for constructing an equivalent inverse cipher with same order steps for encryption, and it's deriving a more efficient implementation. Swapping the byte substitutions and shift rows has no effect, since work just on bytes. Swapping the mixed columns and add round key steps requires the inverse of mixed columns steps to be applied to the round keys first. This makes the decryption schedule a little more complex with this construction. AES decryption is not identical to encryption since steps done in reverse, but can define an equivalent inverse cipher with steps as for encryption, but using inverses of each step with a different key schedule. Works since result is unchanged. Swap byte substitution and shift row. Works since result is unchanged. Swap mixed columns and add, that is tweak round. RC4 stream cipher. In this video, we are going to see about RC4 stream cipher. RC4 is a stream cipher designed in 1987 by Ron Rivers for RSA security. It is a variable key size stream cipher with byte-oriented operations. The algorithm is based on the use of a random permutation. Analysis shows that the period of the cipher is overwhelmingly likely to be greater than 10 power 100. 8 to 16 machine operations are required per output byte, and the cipher can be expected to run very quickly in software. RC4 is probably the most widely used stream cipher because of its simple but effective variable key size byte-oriented operations. It is used in the SSL or TLS secure web protocol and in the WEP and WPA wireless LAN security protocols. RC4 was kept as a trade secret by RSA security, but in September 1994 was anonymously posted on the internet on the Cypherpunks anonymous remailers list. The RC4 key is used to form a random permutation of all 8-bit values. It then uses that permutation to scramble input info processed a byte at a time. Uses of RC4. RC4 is used in a number of applications currently. One of its most important uses is in SSL, also known as TLS, which is used to secure most of the world's electronic commerce over the World Wide Web. It is also used in WEP, the IEEE 802.11 wireless networking security standard. It can also be found in a number of other applications, including email encryption products. RC4 key schedule. The RC4 key schedule initializes the state S to the numbers 0 and so on up to 255 and then walks through each entry in turn, using its current value plus the next byte of key to pick another entry in the array and swaps their values over. After doing this 256 times, the result is a well and truly shuffled array. S forms internal state of the cipher. The total number of possible states is 256 factorial, a truly enormous number, much larger even than the 2048-bit, that is 256 into 8 max key allowed can select. For I is equal to 0 to 255, do S of I is equal to I, T of I is equal to K of I mod key len, J is equal to 0. For I is equal to 0 to 255, do J is equal to J plus S of I plus T of I mod 256. Swap S of I, S of J. RC4 key stream generator. The RC4 key stream generator works by continually shuffling the permutation stored in S as time goes on, each time picking a different value from the S permutation as output. One round of RC4 outputs an n-bit word as key stream, which can then be XORed with a plain text to produce the ciphertext. Initialization. I is equal to 0, J is equal to 0. Generation loop. I is congruent to I plus 1, J is congruent to J plus S of I. Swap S of I, S of J. Output Z is equal to S into S of I plus S of J. RC4 encryption or decryption. To form the stream key for encryption or decryption, which are identical, RC4 continues to shuffle the permutation array S by continuing to swap each element in turn with some other entry and using the sum of these two entry values to select another value from the permutation to use as the stream key, which is then XORed with the current message byte. I is equal to J is equal to 0. For each message byte MI, I is equal to I plus 1 mod 256, J is equal to J plus S of I mod 256, swap S of I, S of J, T is equal to S of I plus S of J mod 256, Ci is equal to Mi XOR S of T. RC4 security. RC4 is claimed to be secure against known attacks, have some analysis, none practical. Result is very non-linear since RC4 is a stream cipher, must never reuse a key. Currently, RC4 is regarded as quite secure if used correctly with a sufficiently large key. Perfect security. In this video, we are going to learn about perfect security. A crypto system has perfect secrecy if for any message X and any encipherment Y, P of X by Y is equal to P of X. This implies that there must be for any message cipher pair at least one key that connects them. Hence, modulus of K is greater than or equal to modulus of C, which is greater than or equal to modulus of P. Shannon perfect security. Theorem. Suppose a crypto system with modulus of K is equal to modulus of C is equal to modulus of P. The crypto system has perfect secrecy if and only if each key is used with equal probability 1 by modulus of K for every plain text X and ciphertext Y. There is a unique key K such that EK of X is equal to Y. Proof. Suppose perfect secrecy, that is P of X by Y is equal to P of X for all X and Y. Unless P of X is equal to 0, there must be enough keys so that any ciphertext can be decoded as a given plain text, that is K is greater than or equal to modulus C, but by supposition, equality must hold. Hence, there is a unique key for every XY pair. Suppose keys K1, K2 and so on are the unique keys such that dki of Y is equal to xi. Using Bayes' law, P of xi by Y is equal to P of Y by xi into P of xi the whole divided by P of Y. Using the assumption of perfect secrecy, we have P of Y by xi is equal to P of Y. Hence, each ki must occur with the same probability. We now assume that P of k is equal to 1 by modulus of k and that there is a unique key relating any plaintext ciphertext pair. P of x by y is equal to P of y by x into P of x, the whole divided by P of y. By the uniqueness of keys, P of y by x is equal to 1 by modulus of k. We also calculate P of y is equal to sum k, P of k into P of dk of y is equal to 1 by modulus of k sum k P of dk of y is equal to 1 by modulus of k sum x P of x, which is equal to 1 by modulus of k. Cancelling the 1 by modulus of k gives the result P of x by y is equal to P of x, that is perfect secrecy. When keys are uniformly chosen in a cipher, a deterministic cipher has Shannon security. The number of keys encrypting M to C is the same for any pair of MC. Basic idea: ciphertext should provide no information about plaintext. Have several equivalent formulations. The two random variables M and C are independent. Observing what value C takes does not change the distribution M. Knowing what value of M does not change the distribution of C. Encrypting two different messages M0 and M1 results in exactly the same distribution. Cipher machines, that is rotor machines. In this video, we are going to learn about cipher machines. Before modern ciphers, rotor machines were most common product cipher. Rotor machines used a series of cylinders, each giving one substitution, which is rotated and changed after each letter was encrypted. With 3 cylinders, have 26 power 3 is equal to 17,576 alphabets. The example just given suggests that multiple stages of encryption can produce an algorithm that is significantly more difficult to cryptanalyze. This is as true of substitution ciphers as it is of transposition ciphers. Before the introduction of DES, the most important application of the principle of multiple stages of encryption was a class of systems known as rotor machines. The machine consists of a set of independently rotating cylinders through which electrical pulses can flow. Each cylinder has 26 input pins and 26 output pins, with internal wiring that connects each input pin to a unique output pin. For simplicity, only 3 of the internal connections in each cylinder are shown. If we associate each input and output pin with a letter of the alphabet, then a single cylinder defines a monoalphabetic substitution. If an operator depresses the key for a letter A, an electrical signal is applied to the first pin of the first cylinder and flows through the internal connection to the 25th output pin. Consider a machine with a single cylinder. After each input key is depressed, the cylinder rotates one position so that the internal connections are shifted accordingly. Thus, a different monoalphabetic substitution cipher is defined. After 26 letters of plaintext, the cylinder would be back to the initial position. Thus, we have a polyalphabetic substitution algorithm with a period of 26. A single cylinder system is trivial and does not present a formidable cryptanalytic task. The power of the rotor machine is in the use of multiple cylinders in which the output pins of one cylinder are connected to the input pins of the next. The left half of the figure shows a position in which the input from the operator to the first pin, that is plain text letter A, is routed through the 3 cylinders to appear at the output of the second pin, that is ciphertext letter B. With multiple cylinders, the one closest to the operator input rotates one pin position with each keystroke. For every complete rotation of the inner cylinder, the middle cylinder rotates one pin position. Finally, for every complete rotation of the middle cylinder, the outer cylinder rotates one pin position. This is the same type of operation seen with an odometer. The result is that there is 26 into 26 into 26 is equal to 17,576 different substitution alphabets used before the system repeats. The addition of 4th and 5th rotor results in periods of 4,56,976 and 1,18,81,376 letters respectively. This general solution would need about 50 letters per cipher alphabet, meaning that all 5 rotors would have to go through their combined cycle 50 times. Electronic Codebook ECB mode. In this video, we are going to see about electronic codebook, that is ECB mode. The simplest mode is the electronic codebook ECB mode, in which plaintext is handled 64 bits at a time and each block of plaintext is encrypted using the same key. The term codebook is used because for a given key, there is a unique ciphertext for every 64-bit block of plaintext. Therefore, one can imagine a gigantic codebook in which there is an entry for every possible 64-bit plaintext pattern showing its corresponding ciphertext. For a message longer than 64 bits, the procedure is simply to break the message into 64-bit blocks, padding the last block if necessary. Decryption is performed one block at a time, always using the same key. The ECB method is ideal for a short amount of data, such as an encryption key. Thus, if you want to transmit a DES key securely, ECB is the appropriate mode to use. The most significant characteristics of ECB is that the same 64-bit block of plaintext, if it is known that the message always starts out with certain predefined fields, then the cryptanalyst may have a number of known plaintext ciphertext pairs to work with. If the message has repetitive elements with a period of repetition of multiple of 64 bits, then these elements can be identified by the analyst. This may help in the analysis or may provide an opportunity for substituting or rearranging blocks. Advantages and limitations of electronic codebook ECB mode. ECB is not appropriate for any quantity of data since repetitions can be seen, especially with graphics, because the blocks can be shuffled or inserted without affecting encryption or decryption of each block. Its main use is to send one or a very few blocks, example, a session encryption key. Repetitions in message may show in ciphertext. If aligned with message block, particularly with data such as graphics or with messages that change very little, which become a codebook analysis problem. Weakness due to encrypted message blocks being independent. Main use is sending a few blocks of data. Cipher block chaining CBC mode. In this video, we are going to see about cipher block chaining CBC mode. To overcome the security deficiencies of ECB, we would like a technique in which the same plaintext block, if repeated, produce different ciphertext blocks. A simple way to satisfy this requirement is the cipher block chaining CBC mode. In this scheme, the input to the encryption algorithm is the XOR of the current plaintext block and the preceding ciphertext block. The same key is used for each block. In effect, we have chained together the processing of sequence of plaintext blocks. The input to the encryption function for each plaintext block bears no fixed relationship to the plaintext block. Therefore, repeating patterns of 64 bits are not exposed. For decryption, each cipher block is passed through the decryption algorithm. The result is XORed with the preceding ciphertext block to produce the plaintext block. To see that this works, we can write then Cn is equal to Ek of Cn-1 XOR P. Dk of Cn is equal to Dk of Ek of Cn-1 XOR Pn. Dk of Cn is equal to Cn-1 XOR Pn. Cn-1 XOR Dk of Cn is equal to Cn-1 XOR Cn-1 XOR Pn, which is equal to Pn. To produce the first block of ciphertext, an initialization vector IV is XORed with the first block of plaintext. On decryption, the IV is XORed with the output of the decryption algorithm to recover the first block of plaintext. The IV must be known to both the sender and receiver. For maximum security, the IV should be protected as well as the key. This could be done by sending the IV using ECB encryption. One reason for protecting the IV is as follows. If an opponent is able to fool the receiver into using a different value for IV, then the opponent is able to invert selected bits in the first block of plaintext. To see this, consider the following. C1 is equal to Ek of IV XOR P. P1 is equal to IV XOR Dk of C1. Now use the notation that X of I denotes the ith bit of the 64-bit quantity X. Then P1 of I is equal to IV of I XOR Dk of C1 of I. Then using the properties of XOR, we can state P1 of I dash is equal to IV of I dash XOR Dk of C1 into I. This means that if an opponent can predictably change bits in IV, the corresponding bits of the receiver value of P1 can be changed. It is an appropriate mode for encrypting messages of length greater than 63 bits. In addition to its use to achieve confidently, the CBC mode can be used for authentication. Advantages and limitations of cipher block chaining CBC mode. The chaining provides an avalanche effect, which means the encrypted message cannot be changed or rearranged without totally destroying the subsequent data. However, there is the issue of ensuring that the IV is either fixed or sent encrypted in ECB mode to stop attacks on first block. Each ciphertext block depends on all message blocks. Thus, a change in the message affects all ciphertext blocks after the change as well as the original block. Initial value should be known to sender and receiver. However, IV is sent in the clear. An attacker can change bits of the first block and change IV to compensate. Hence, either IV must be a fixed value or it must be sent encrypted in ECB mode before rest of the message. Cipher feedback mode, CFB mode. In this video, we are going to see about cipher feedback, that is CFB mode. The DES scheme is essentially a block cipher technique that uses 64-bit blocks. However, it is possible to convert DES into a stream cipher using either the cipher feedback CFB or the output feedback mode. A stream cipher eliminates the need to pad a message to be an integral number of blocks. It also can operate in real time. Thus, if a character stream is being transmitted, each character can be encrypted and transmitted immediately using a character-oriented stream cipher. One desirable property of a stream cipher is that the ciphertext be of the same length as the plaintext. Thus, if 8-bit characters are being transmitted, each character should be encrypted using 8 bits. If more than 8 bits are used, transmission capacity is wasted. For decryption, the same scheme is used except that the received ciphertext unit is XORed with the output of the encryption function to produce the plaintext unit. This is easily explained. Let Sj of x be defined as the most significant j bits of x. Then Ci is equal to Pi XOR with Sj of e of iv. Therefore, Pi is equal to Ci XOR with S of e of iv. The same reasoning holds for subsequent steps in the process. In addition to its use to achieve confidentiality, the CFB mode can be used for authentication. Advantages and limitations of cipher feedback mode, CFB mode. CFB is the usual stream mode as long as can keep up with the input, doing encryptions every 8 bits that is appropriate when data arrives in bits or bytes. A possible problem is that if it is used over a noisy link, then any corrupted bit will destroy values in the current and next blocks, since the current block feeds as input to create the random bits for the next. Limitation is need to stall after every n bits of block encryption. The block cipher is used in encryption mode at both ends. Errors propagate for several blocks after the error in current block. Output feedback mode, OFB mode. In this video, we are going to see about output feedback mode, OFB mode. The output feedback OFB mode is similar in structure to that of CFB. It is the output of the encryption function that is feedback to the shift register in OFB, whereas in CFB, the ciphertext unit is feedback to the shift register. For example, if a bit error occurs in C, only the recovered value of P is affected. Subsequent plaintext units are not corrupted. With CFB, C also serves as input to the shift register and therefore causes additional corruption downstream. Consider that complementing a bit in the ciphertext complements the corresponding bit in the recovered plaintext. Thus, controlled changes to the recovered plaintext can be made. This may make it possible for an opponent, by making the necessary changes to the checksum portion of the message as well as to the data portion, to alter the ciphertext in such a way that it is not detected by an error-correcting code. Advantages and limitations of output feedback mode, OFB mode. One advantage of the OFB mode is that bit errors in transmission do not propagate. Used when error feedback a problem or where need to encryptions before message is available. Superficially similar to CFB, but feedback is from the output of cipher and is independent of message. The disadvantage of OFB is that it is more vulnerable to a message stream modification attack than in CFB. Since OFB is a Vernam cipher variant, the stream should never be used more than once, otherwise the two ciphertexts can be combined, cancelling these bits and leaving a book cipher to solve. And sender and receiver need to remain in sync or all data is lost. Originally specified with m-bit feedback in the standards. Subsequent research has shown that only OFB64 should ever be used. Counter CTR mode. In this video, we are going to see about counter, that is CTR mode. The counter CTR mode is a variant of OFB which encrypts a counter value and hence the name. It has been standardized for use with AES along with the other existing 4 modes. It is being used with applications in ATM, that is Asynchronous Transfer Mode, Network Security, and IPsec, that is IP Security. A counter equal to the plaintext block size is used. The only requirement stated in SP 838A is that the counter value must be different for each plaintext block that is encrypted. Typically, the counter is initialized to some value and then incremented by 1 for each subsequent block. Similar to OFB but encrypts counter value rather than any feedback value, must have a different key and counter value for every plaintext block, never reused. CI is equal to PI XOR OI. OI is equal to DES K1 of I. Uses high-speed network encryptions. Advantages and limitations of counter, that is CTR mode. CTR mode has a number of advantages in parallel hardware and software efficiency, can pre-process the output values in advance of needing to encrypt, can get random access to encrypted data blocks, and is simple. In terms of efficiency, can do parallel encryptions in advance of need, good for bursty high-speed links, random access to encrypted data blocks, provable security, good as other modes. But must ensure never reuse key or counter values, otherwise could break. OFB. Comparison of modes. In this video, we are going to see about comparison of modes. Mode, description, typical application. ECB. Each block of 64 plaintext bits is encoded independently using the same key. Secure transmission of single values, for example, an encryption key. CBC. The input to the encryption algorithm is the XOR of the next 64 bits of ciphertext. General purpose block-oriented transmission. CFB. Input is processed G bits at a time. Preceding ciphertext is used as input to encryption algorithm to produce pseudo-random output, which is XORed with plaintext to produce next unit of ciphertext. Authentication and confidentiality. OFB. Similar to CFB, except that the input to the encryption algorithm is the preceding DES output. Stream-oriented transmission over noisy channel, for example, satellite communication. CTR. Key calculated using the nonce and the counter value. Counter is incremented for each block. General purpose block-oriented transmission used for high-speed communications.